About ready? I won't start it till you say you're ready.
Looks like I'm ready.
Let's go.
All right, let's kick it off. This is going to be a bit of a change from what we've seen so far, a little bit more traditional machine learning, but I hope everyone is still just as interested. All right, so for those of you out there who have built a machine learning model ever in your careers, I'm sure you're familiar with this scenario. You're going through, you collected your data, you've cleaned it up, you're, trained your first model, you check it against a bunch of benchmarks and things like that, right? And you're super psyched, the model's working well, you push it out to production, and what happens, right? No model ever survives its first encounter with the customer. So, customer complaints start rolling in, your model's making some mistakes here and there, your boss comes to you and says, fix it. So you're thinking to yourself, well, I already made a good model, how do I fix it, right? So you can go around Google online, you'll see a bunch of great tips for what to do, things like feature engineering and gather more data and all those things, which are true, but they don't tell you which data to gather, which features to engineer, things like that. And that's where data maps come into play. This is a concept that I learned about only last year. As far as I can tell, it first came about in 2020 in this paper. And basically what the authors of this paper did was take all of their training data that they used to train a model and calculated 3 different coefficients for it: the confidence, the variability, and the correctness. And by using these coefficients and making this plot, you can see that the data actually clusters itself really well into 3 sort of large categories. You've got the data that is very easy to learn from. This is the good stuff. This is what's helping your model understand what it's supposed to be doing. On the sort of opposite end of the spectrum there, you've got the data that's hard to learn from. So basically, you're not learning from any of this. And as we'll see in an example, that's probably where you're going to see a lot of mislabeled data points. And so you're going to want to look at that data much more closely. And then finally, the third category here, we've got this ambiguous data. It sounds like it might be a lot like the hard to learn data. You might want to throw that away as well, but hold on, because what we'll actually find is that ambiguous data has a use as well. So we've got these 3 coefficients. How do we calculate them? For those of you who speak math out there in the audience, here are the equations that one would use. These are pulled straight from the paper, but I'll explain them in words as well here. So for correctness, what you're going to do essentially is, as you're going through and you're training your model over multiple epochs, and the model is seeing the same data point multiple times, as those of you know who have built models, there's a step in the model training process where the model makes a naive prediction, and you test it against ground truth, and then you go back and adjust your weights, depending on if your prediction was correct or not. So what you're going to do is store all of those predictions that your model made. So say you're going over 10 epochs, you'll store how many times did that prediction match the ground truth, and then divide by the number of epochs. Super simple math, very easy to compute, not going to take up a lot of compute time. Okay, next one, confidence. So for this technique to work, you're going to have to use a machine learning model that's going to spit out a confidence. And all you're going to do is, again, as the model's going through over multiple epochs, for each one of your data points, you're going to save off how confident was the model when it was making that prediction that we talked about earlier. And finally, variability looks like the most complicated equation, might actually be the most easiest one to explain verbally. All variability is telling you is how often is your model changing its mind. So if you're doing a binary classifier, how often is it changing back and forth between true and false? Or multi-label, how often is it switching classes or labels or that sort of thing? So that's it. That's all you need to calculate. You can build your own data map, and I'm going to go into a little example of having done it myself. So for this example, I went and grabbed this Go Emotions data set you can grab off of Hugging Face. It's got about 60,000 Reddit comments, and humans have gone through and labeled each one of the comments with an emotion. For this example, we're going to ignore most of the categories, and we're going to just build a binary predictor to determine if a snippet of text, a Reddit comment, is expressing gratitude or anything else. So gratitude or not gratitude. That's all we're going to try to determine here. As I mentioned before, we're going to do a classifier, so we're going to use stochastic gradient descent. It's really fast, really easy to use for this, and we're going to train it over 10 epochs. And we get this data map that you see here. And conveniently enough, it actually matches the structure of the paper's data map as well. We can see we have a lot of this really easy to learn from data up there. That's the majority class. That's not the non-gratitude stuff for the most part. We've got some hard to learn data points that are down here. We're going to go into what those look like. We're going to inspect some of them. And then in this instance, there's a much thinner line of the ambiguous data, but that is present as well. Okay, so we built our data map. Let's dive into some of these data points and see what the model is doing and kind of get a sense of what the model's thinking. I'm going to anthropomorphize a lot here, so get used to it. All right, so these are text snippets from the data set that were easy for the model to classify. And these are expressing gratitude. And what we see is the word thanks or thank you appears in basically every one of them, right? So this is a fantastic sanity check. This shows that the model is learning what we're hoping it would learn, and what it's doing, the decisions that it's making, make sense to us as humans. We're not going to get a lot more out of actually diving deep into all these data points, but this is a nice sanity check to look at. Where the real information and sort of the map part of the data map comes in is when we start looking at some of the ambiguous and some of the hard to classify samples. So on your ambiguous, for folks who can't read them all the way back there, we've got stuff like Happy New Year's, congrats, vegan baking is still daunting, but I'll conquer it one day. A lot of text snippets that I as a human might actually have some difficulty classifying. And not only that, they may be expressing joy or other positive emotions, but not specifically gratitude. So one would understand why maybe the humans might have struggled to do this and why the model is struggling to do this. You're going to want to hold on to these data points though, because as you send your model out to production, and when it sees out of distribution data or unseen data points or new things, being able to train and understand these ambiguous data points is really going to help that model performance when it's out there in the real world, getting everything thrown at it. So this stuff's good, keep it around. The hard to classify stuff. We see phrases like love the homeless encampment in this photo. And again, these were labels as gratitude by humans. So what we've learned already is that humans are just as good as computers are at understanding sarcasm. We've also got some other phrases here that are just clearly not gratitude. So these were mislabeled. Whatever the human did, they did it wrong. And so no wonder the model is struggling to try to understand it. It's trying to label this as gratitude, and there's no gratitude in there. And so what you're doing is actually harming your model's performance to learn and understand by giving it the wrong information. Okay, as a quick hack, one thing you could do once you've done all of this is, let's say we take that model, here's the before score. We see it's already doing pretty well. For the sake of time, I'm just going to focus on the accuracy or the weighted average. They're going to be the same value here. What we see is that the model is already doing a pretty reasonably good job of identifying gratitude. But if we throw away all of those hard to classify data points that are misleading the model and retain 80% of the ambiguous data, because we do want some of those edge cases, we see that we're able to get a 0.01 improvement in accuracy or weighted average. So we've basically gone from 98% accuracy to 99% accuracy without doing anything extra in terms of work. We basically just got this for free. Okay, since I'm running out of time, I'll go to the summary real quick. Leave this up here. If you're out there and you're building models and you need to improve them, data maps are a great technique that you can utilize in order to do that. And if you really want to, you can hack your way to a better Kaggle score by just throwing away all that hard to use data instead of fixing it. All right. So data maps are your treasure map to understanding your data and using it better. And if you are looking for treasure out there, I will just say I'm on the job market. So if you need a data science manager or leader, definitely come talk to me after all of this. Thanks.
All right. Thank you, Jim. Well done. Well done. You got Wesley.
What did you do on your summer break?